In this video, we're going to look at biasing the transistor by setting the voltage at the gate. As we've seen, that to use a transistor as an amplifier, we need to place it in a state, we call it a bias position, or we bias the transistor, where there is a nearly linear relationship between the gate voltage VGS and the current flowing through the transistor I sub D. So the bias point then becomes this point marked Q here. Q stands for quiescent. Quiescent means resting. We're basically putting in the transistor into a state where there is a DC current flowing through it at a certain DC voltage, and then we allow the voltage to vary away from that quiescent or bias point, and that voltage small variation then sees itself or manifests itself in a larger variation across the output of the transistor, and that's where we get this gain. So setting the bias point involves setting VGS, the voltage from the gate to the source, the current through the transistor, and in the process we also establish the bias or the quiescent or the resting VDS. As we've derived, in saturation, ignoring the early effects while doing our DC calculations, I sub D, the drain current, is given by this equation that we're becoming pretty familiar with. 1/2 mu sub n COX, and we've got the aspect ratio W over L times VGS minus VT quantity squared. One way of setting this point VGS, which is the gate to source voltage of our quiescent point, is by setting the voltage at the gate itself using a voltage divider. Tying a couple of resistors to the positive power supply, we'll call this RG1 and this down here RG2, we establish a voltage division between the source and ground, and then the gate is tied to that subdivided portion of VDD. Doing so makes VGS very stable and independent of variations in the transistor. But while I sub D is a function of VGS, it's also a function of the transistor parameters mu sub n, COX, and the aspect ratio. And in the manufacturing process, there can be a fair amount of variation between the width, or variation in the width and the length of the transistor, the actual physical process of creating those. There's going to be some variation in it. COX, the capacitance at the due to the oxide of the gate, is dependent upon the thickness of that oxide, and there can be variations in that in the manufacturing. So there's manufacturing variations or variations in I sub D due to the manufacturing process, but there are also, in addition to those, variations in I sub D due to changes in the temperature of the transistor. Mu sub n, the mobility of the electrons in the channel, is a function of temperature. V sub t, the threshold voltage, is a function of temperature. So we see that there's some uncontrollable variation in I sub D, both due to manufacturing process in precision, and then also due to the ambient temperature that the transistor is acting in. I sub D then is going to change beyond our control, and in the process moving the transistor from its intended bias point. If VGS doesn't also vary, we run into a situation that we see here. Two different devices operating perhaps with different manufacturing precision, or even the same two different devices coming off of the same manufacturing process, there is imprecision in the manufacturing process, and so I sub D, the dependence on that, will vary. And those two different devices may well have two different curves relating VGS to I sub D. So if VGS is stationary, having been established by the power supply and two resistors, VGS really isn't going to move very much. And for two different transistors, we see significantly different bias values for I sub D, and it places them into different positions, relative positions on the curves themselves. We saw in a previous video that instead of just tying the source to ground, if we place a source resistor between the source and ground, this source resistor will provide negative feedback and tend to counteract or control the variations in I sub d that we've just been talking about. If for any of these reasons I sub d increases from its designed value, I sub d getting bigger, the voltage drop across R sub s increases, reducing VGS. Again, V sub g then would be set by the voltage divider, and V sub g becomes stationary. By putting this resistor here, as I sub d increases, the voltage across here increases, which then reduces VGS and pushes I sub d back towards its intended state. Similarly, unintended decreases in I sub d are constrained, as V across R sub s then would decrease, again, which would then allow VGS to increase, which would then increase I sub d. So let's understand what's happening here. Without R sub s, VGS equals V sub g. Without the feedback resistor, VGS, the voltage from the gate to the source, is simply equal to the pegged voltage V sub g. It doesn't react to changes in I sub d. But with R sub s in place, the gate voltage VGS, or the V sub g, this voltage here, is split across the gate to source and the resistor here. Or in other words, we've got then that VGS, the voltage from the gate to the source, is equal to V sub g minus I sub d times R sub s. VGS, the voltage here, is inversely dependent on I sub d. So the VGS that's up here in this equation here, that I sub d is dependent upon, this VGS decreases as I sub d gets bigger. And similarly, VGS gets bigger as I sub d gets smaller. If we solve this for I sub d, we get then that I sub d is equal to V sub g minus VGS over R sub s. Or putting it into the slope-intercept form, we have then I sub d is equal to negative 1 over R sub s plus V sub g over R sub s. I left out the VGS term here, VGS. Let me write that over again. Let me write it over here. We end up with then I sub d is equal to negative 1 over R sub s times VGS plus V sub g over R sub s. Instead of being rigidly controlled, VGS then varies in the opposite direction to I sub d. As I sub d gets bigger, VGS gets smaller, making I sub d get smaller. This equation right here becomes the equation for what is known as the load line. This equation relating I sub d and VGS draws a new line onto our graph here. And as you can see, where in the past VGS was constant and represented large variations in I sub d, we can now allow VGS, or not allow it, but VGS now moves somewhat according to this line and results in significantly reduced variations in I sub d. Or conversely, variations in I sub d are constrained by this movement of VGS. Let's look at two different scenarios where R sub s is used to stabilize the bias point. First, if only one power supply is available, a positive VDD, and at the other side we've got ground, V sub g is lifted above ground and positioned somewhere between ground and VDD using the voltage divider here. As we've already described, R sub S then provides the negative feedback to stabilize this bias point. Generally speaking, because the bias is not at ground, but the bias is up above ground, a coupling capacitor is inserted between this stage and either the source or a previous stage, so that if there's any DC component to the circuit ahead of our amplifier, which might impact the bias of our amplifier, is removed. Let's say that again. Any DC component that might be present in either the signal coming in that we're wanting to amplify or being introduced by a previous stage, if there's any DC component in that, that would have the effect of changing our DC bias. It would be potentially move V sub G. So a coupling capacitor is placed right ahead of the amplifier stage to remove any DC component. If you have two power supplies present, a positive and a negative, then the gate voltage can be placed somewhere and typically tied to ground through some resistor R sub G, so the gate voltage sits at 0, and because we've got a negative voltage, VGS then drops it down to a point. This then would be at a point below 0. But we still have R sub S in play to stabilize the any variations in I sub D. Since the current going into the gate is 0, this resistor, there will be no voltage drop across it, no current through it, and it provides then the reference point here to ground. Generally, this R sub G, this gate resistance, will be kept relatively large so that in the small signal model, where we're wanting to bring that small signal in and have it still see a large impedance, we don't want there to be a low impedance or a low resistance path to ground that would cause attenuation of that signal. So R sub G is typically kept pretty large. Once the bias gate voltage is established, a design rule of thumb for setting I sub D is to make it so that about 1/3 of your total voltage is dropped across R sub D, another third of it is dropped across R sub S, and that leaves then 1/3 of your total voltage swing to be dropped across the transistor in VDS. So 1/3 here, 1/3 here, and 1/3 across the transistor. Because the current is the same through both R sub D and R sub S, that generally means that R sub D and R sub S will be equal to each other.